All right, let's talk about one of the greatest minds in engineering and physics, and that is Sir Isaac Newton, who developed the Newton's laws. And I'm sure you heard about them before and you have dealt with them before. But let's find a common ground here and let's talk a little bit about the idea of forces. So, what does it take to describe a force? And then I want to talk a little bit about the history. When I talk about the individual Newton's laws, so I'm going to talk about Newton's first, Newton's second, and Newton's third law, and then also the law of gravitational attraction, which is very important. But first, let's think about forces. So we need, depending on who you ask, we need two, or some people would say three quantities to fully describe a force. So you cannot just use a single number is the point here, right? A single number would be called a scalar, and you can use that to describe, for example, a temperature or a volume or something like that. But if you have a force in, let's say, a coordinate system, let's draw a coordinate system here. So I have like an XY coordinate system, and in that XY coordinate system, I want to have a force, and my force needs a length, right? So that would be one number that needs to describe that. And I need a direction, which is really defined by the arrowhead. And some people would argue, this is where the 2 or 3 comes from, that you also would need an angle, although you could argue that's by the direction defined. So it really depends on which philosophy you want to use, but you need to describe it with more than one number. And of course, you know this already. You know that you need to use vectors for that. But this wasn't always clear to every physicist out there. In fact, Sir Isaac Newton worked his way through that, and in the process, he actually developed the calculus for it. So we actually need vector calculus. Without that, we would be lost, and that's why we spend a lot of time in the early part of this lecture to talk about vector calculus. So we need more than scalars is the point here, and we need to understand how to deal with these vectors. And the first documented case that we know of nowadays that thought about forces and how they act are actually traced back to Aristotle, right? So you obviously heard that name before. And he really lived between 384 and 322 BC. And so it goes back a very long time. But the reason I'm mentioning him here is because he assumed that as soon as an object stops moving, there's no force acting on it. So he thought that no force, no movement. No force, no movement. And if you remember your physics class, then you already know that this is not considered true anymore, because we then had actually Galileo Galilei, and he lived between 1564 and 1642. And he actually was the first one to recognize that it requires a force to bring an object to a halt. So force needed to stop an object. And honestly, I don't know why Newton gets away with his first law here, because he literally stand on the shoulder of giants here. He pretty much took the same idea that Galileo Galilei already used and turned it into his first law of motion. And so Isaac Newton really came along, and let's write that down as well, that Isaac Newton, who coincidentally actually lived between 1642, so right when Galileo Galilei died, to 1727. And in that time, he published a book called Philosophia Naturalis Principia Mathematica. And you can actually find a copy of that in the National Library online as well. And that is the book that claims to have invented calculus. Some people say that it was Leibniz who came up with calculus, but of course, as engineers, we believe that it was Newton. I don't know if that's true or not, but I choose to believe that. Anyways, in that book, he introduced some laws that we still use today. And what I find important to appreciate is that he came up with calculus. We sometimes complain about the things that we have to learn in school and that it's so difficult to solve these problems. This guy, Newton, actually wanted to solve a problem and didn't have the tools at the time, so he had to invent calculus. Can you imagine that? Inventing calculus to solve a problem, which he obviously successfully did at that time, but he had to invent the tools too. I think that's amazing. So more power to him. So let's talk about the laws, the first law first, and what it describes. And there are some definitions, you can look them up online. Galileo pretty much said that a body at rest remains at rest and the body in motion continues to move at a constant velocity unless acted upon by an internal force. And Newton pretty much stated the same. Let's maybe write that one down. He said that every body persists in a state of rest or uniform motion in a straight line unless it is compelled to change its state by a force impressed thereon. So that's how Newton reformulated Galileo Galilei's first assumption, and effectively they say the same thing. But what does that really mean? In consequence, that means to change a state is really dependent on how resistant a body is, right? So some bodies can be more resistant than others, and you know this is called inertia. So some bodies have high inertia and some bodies have small inertia. So in the classroom, usually I show a picture of a big boat, and I'm a great artist, as you will learn throughout the entire semester, but let's pretend this is a boat. And then I have a little fish here, and that fish has much less inertia, so this is small inertia. And this is large inertia. And the large inertia, as you know from everyday life, is very difficult to change in either motion or to bring it to rest. Whereas like if you have an object with like small inertia, then it is easy to change that state. And so the kilogram or the mass is really the measurement of inertia. And that is also something that we know from daily life, right? So large mass, large inertia. Large mass, large inertia. And that is because it's very difficult to change that state. However, we are now moving into Newton's second and third law. And before we do that, I want you to appreciate that, like, if these two swim into each other, and maybe my artist skills here should add some waterline here. So let's say there's some water there. And if they swim into each other and they touch each other, you may think that the fish actually pushes away from the boat, but in reality, the boat also pushes away from the fish. And that is something you should not underestimate, not because something is larger, it's kind of still relative to the small part. From an engineering standpoint, you always need to understand that both have an effect on each other if they hit each other, for example. But we will talk about that when we talk about Newton's third law. Let's first talk about Newton's second law. So for Newton's second law, that is something you obviously have used before, and that is force. It describes the force, and it says that force is equal to mass multiplied by its acceleration. And that is the reason why we need vectors. Because we know that the mass is really an integer, right? You can describe the mass by an integer. But the acceleration needs to be defined by a vector. Because acceleration is directed, it has a direction. And so what are the units here? The units are mass in kilogram. And then here we have meter per second square. And therefore we know that the force is really kilograms times meter per second square. And because that was defined by Isaac Newton, this unit actually became the Newton, right? So 1 Newton is equal to 1 kilogram multiplied by 1 meter divided by 1 second square. And I always invite my students in the classroom to explain to me what that unit really means and if they can have a feel for that. What is 1 Newton? It's kind of difficult to conceptualize initially what 1 Newton really is. And the story, of course, goes that Newton had this idea when an apple hit his head, and that is something that works. But in the classroom, and I wish I could do this right now, but sorry, we can't do this here. In the classroom, I hand out chocolate, and I like to hand out German chocolate, because German chocolate is usually delivered in 100 gram packages, right? 100 gram is one chocolate, one German chocolate, if you will. And so I encourage my student to really eat that chocolate, enjoy it, and never forget that it's 100 grams. And that is roughly speaking, actually in mechanics, it's exactly speaking 1 Newton. So please understand what 1 Newton is. And you may think, hey, I have heard about Newtons before, I dealt with them before, but all the time in the classroom, I find that students have no concept of what 1 Newton is, or what is 10 Newton, or what is 50 Newton, or a kilonewton. But you can always relate it back to the 1 chocolate, and you know that you can lift a chocolate, you can eat a chocolate, but you may know that you cannot lift 10 million chocolates, for example, and so on. So you can always take that back to the basics. And in fact, I will in a second take this to the specific weight of water, something we can also trace back to this concept. But before I do that, I just want to emphasize one more time on this force is equal to mass times acceleration. And that is because it's intuitively pleasing to think of this, right? So the stronger the force on an object, so the higher the force, the more it accelerates. Let's write that down. So more force leads to more acceleration. And you know that, right? You can try this. Take, I don't know, your house keys and throw them with a little force or throw them with high force. And you will see that they obviously accelerate differently. Likewise, you know that if you have something with more mass, then it is more difficult to change the acceleration. So more resistance to acceleration. And you can try this too. Try throwing your key or try throwing your desk, right? Both of them have different mass, and the one with the lower mass probably accelerates easier. And this is all found in this equation. And again, the unit is kilograms times meter per second square, but really we call that 1 Newton. Now, we already talked about the fact that 1 liter of water, 1 liter of water is equal to 1 kilogram. And so we know now that 1 kilogram is equal to 1,000 grams. And therefore we know that 1 liter of water really is 10 Newton, right? Because it's 1 kilogram. So 10 Newton per 1 liter of water. And why am I telling you this? Because in this class, take this as a word of advice, in this class and later on in engineering, you will see many problems where you have to fill a volume with water. And we will not tell you what the force is on the system. We will just tell you, hey, there is 1 cubic meter of water, or there's 500 liters of water in the system. So how many newtons do you have? And the best thing that you should find out, take this as a homework, is how many kilonewton per cubic meter of water do you have? So I want to know from you what that is. If you have 1 cubic meter of water, so 1 cubic meter of water produces how many kilonewtons? Because this is the unit that you will see over and over again later on. So you will see problems where you have to deal with forces that have a kilonewton acting on them, and then you will be given a volume in most likely cubic meters, and you can then use the specific weight of water, right? So specific weight means a weight per volume, and keep in mind that this is a weight, kilonewton, right? And in the imperial system, this would be pounds per cubic foot, for example. But here we're dealing with the metric system or the SI system, and so we're looking at kilonewton per cubic meter. And I want to know from you, I could write it here, but I'm not going to do that, but you will see it over and over again. You need to know this, so find this somewhere on the internet or work out your own way here. Find out how many kilonewtons you have in 1 cubic meter of water, right? And that, of course, we do with G being equal to 10 meter per second square, right? So meter per second square. We talked about this in one of the 0 lectures. So please understand that G, the gravitational constant here now, is 10 meter per second square. But this is important. Find out what kilonewton per cubic meter is produced if you have a volume filled with water. All right. I think with that said, we are now ready to move on to Newton's third law, which of course you have used before as well. And you know that every action on a system is equal to an opposite reaction, right? So and that is something which you may think is super easy, but when we come to part 2 is the thing we always violate. Or in other words, every time we lose points on an exam or on a quiz, we will find that we violated this rule. And this happened to me all the time when I was a student. Although we think that this is so easy, it's the easiest thing to overlook, right? So it's kind of stating that the sum of the forces is equal to 0, right? And that is also intuitively pleasing because you experience this in day-to-day life. For example, the chair you're currently most likely sitting on, you push down on it with your weight, but the chair is also pushing back on you. So examples here would be you're sitting or you're standing on the floor. Let's say you stand on the floor, right? You push down on the floor, but the floor is really pushing back in the opposite direction with the same force. Likewise, if you ride your bicycle, you apply force to the pedals and the pedals push back on you. And then also you turn the wheel into motion and the wheel then pushes on the asphalt and the asphalt pushes back, and that's why you move forward. Or like ice skating, right? So if you have ice skating, this is why you need sharp blades, right? Because only those can create the resistance between the ice and the ice skates that you wear so that you can actually push yourself forward. Otherwise, you would not be able to move on the ice. Or the same is true for walking, by the way. Like the only reason you can walk forward is because you push yourself forward, and the resistance or the friction between your shoes or your feet and the ground allows you to move forward. And that is Newton's third law, and we will have a lot of fun with that. So that completes our Newton's laws, and we now have a solid understanding and a base ground for what's coming up. You may think, hey, why did he bore me with this? I learned all about this in physics. And again, if something goes wrong in this class later on, it can mostly be traced back to this equation here or to this concept. And to understand this concept, we also need to understand these. And I want to point out one more time the importance of the density, or in this case, the specific weight of water. So please have that accurately available when it becomes necessary. But now let's move on to Newton's gravitational law.